Hello everyone, and my name is Carlos, and I'm going to present the work a hybrid algorithm for vehicle routing problem with time windows. So as we know, the vehicle routing problem with time windows can be viewed as a harder version of capacitated vehicle routing problem, where each customer not only has a demand for a certain resource, but also a time window, which is an interval during which deliveries can be made. And of course, these time windows constraints impose an additional challenge on top of capacity constraints. And in this work, we propose a math heuristic for solving the VRPTW, which was used by our team for the 12th DIMACS Implementation Challenge. So as the problem has been defined on the previous presentations, I'm just going to gloss over these just to make sure that we're on the same page regarding notation. So, so V prime is a set of customers, K is the number of available vehicles, C is the capacity of the vehicle, and of course we have a graph G whose set of vertices is the set of customers plus the depot, and each arc on the graph has an associate travel cost and travel time. Each customer has a demand DI and the time window and the service time SI. So our proposed approach is a math heuristic. So it's a mix between standard multi-start iterated local search and a set partitioning procedure, which attempts to create a better solution by using routes stored in the memory. And here's the main algorithm. So we start with these two sets, which are empty, which are route pools, which are essentially sets of routes which are going to be filled during the algorithm. And one is the permanent, and the other is a temporary, which is going to be cleaned from time to time. So we perform a construction for every restart, which is a heuristic which attempts to make a solution. We improve that solution by using the ILS math heuristic. And depending on the size of the instance, we perform set partitioning procedure during every restart, or if it's small enough, according to this parameter, we do it only in the end of the algorithm. And during the ILS procedure, we also fill the temporary route pool with routes which were obtained during local search. So I'm going to explain those highlighted procedures. So the first one is the construction. Basically, we start with a partially filled solution, which is generated randomly, where each route contains only one customer or less. And we insert the rest of the customers according to a certain insertion criterion, which is chosen randomly, which can be either the distance from the customer which is going to be inserted and the position where it's going to be inserted, or its actual insertion cost minus a factor that depends on the distance of it to the depot, times a factor gamma, which is a random number in this range. We also use two different random strategies, insertion strategies, which are choosing randomly too. The first one consists in inserting the remaining customers in any route. So the routes are going to grow independently. And the other one, we start from route number one and we fill it until its capacity is full, and we proceed to the next route and so on until all customers are inserted. Now, of course, those methods account for the capacity constraints, but not for the time windows constraints. So we have to apply a penalty to solutions. Just make sure that feasible solutions are better, they have a better cost than solutions which are infeasible in terms of time windows. So the local search procedure, which is one of the main components of ILS, is based on a randomized version of VND heuristic, and it's performed hierarchically. So we start by doing an inter-route neighborhood structure exploration, which involves two different routes. And then after we modify those two routes, we perform an intra-route search, which are moves performed in the same route. And these are the inter-route structures. So basically moving a block of one or two clients between two routes. We've got exchanging positions of two blocks of customers between two different routes, which is the swap. And finally, the two-opt star, which consists in removing two different arcs from two different routes and reconstructing it in the two possible different ways. And the intra-route structures are very similar. So we have exchange, which exchange the positions of two customers in the same route. Reinsertion moves a block of 1 to 3 clients in the same route. And finally, two-opt, we remove two arcs and we rebuild the solution by inverting the segment between those two arcs. So, of course, those moves are trivial to evaluate in terms of capacity constraints and distance, but not in time windows violation in terms of time windows. So the way we do that is we use the subsequence structures proposed by Vidal et al. And I'm not going to be able to delve into how they work, but basically they are based on the idea that those moves I'm showing you, they consist in breaking a route into pieces. And if we are able to compute the violation, the time window violation for sticking those pieces together, then we are able to compute the violation of the resulting routes. For the perturbation, which is also important for ILS, we use two different very simple methods, which are swapping two different customers between two routes, their positions, or exchanging the routes of two customers and inserting them into random positions. One of those procedures is randomly chosen, and it's executed 1 or 3 times, which is also random. To try to make it to improve its performance in terms of time, we use the acceleration structures proposed by Malheiros et al. And basically they try to exploit the very nature of ILS or the traits of VRPTW itself to avoid unnecessary operations. So the first one of them is the memoization move descriptor, which stores the best move for a pair of routes or for a route and a neighborhood structure. So if we stumble upon it again later on, we don't have to export it again because it's on the memory. There is memoization solution descriptor, which stores previously found local optima in the memory. So when we stumble upon one of them again in a later restart, we know that exploring it is probably not worth it because we already perturbed it until the stopping criterion of ILS was met. So it's probably not worth doing it again. And finally, there's feasible search range, which is based on the simple idea that if you have two different customers with disjoint time windows, one of them must come before the other if they're on the same route. So when you're doing local search, you know that you can insert the one that should come before after the one that should come later. So you can avoid doing a lot of move evaluations. And finally, there's the exact site partitioning procedure in which we attempt to build new solutions by using routes stored in the permanent pool and the temporary pool, because interesting routes may appear at different restarts or iterations. So by mixing them together, maybe we can make a better solution. This problem can be formulated as a mixed integer problem, uh, which has a pretty simple mathematical model. So we have this variable lambda r, which tells us if route r was used in the solution, and we're trying to minimize the total cost of the solution. We're forcing every customer to appear exactly once, and we're compromising ourselves a little bit because we're forcing the number of routes to be that of the best solution found, just to attempt to make the model easier to solve. And here's a set partitioning procedure. So we generate the model accordingly. We use the cost of the best solution as a cutoff value. And we also implement an incumbent callback procedure where every time we find a integer solution during the solving process, we try to improve it again by using ILS. And if we can do that, we update the cutoff value. So the algorithm was tested on these settings during the competition. So we were provided with sets of instances which were partitioned into 3 sets, and they were tested. They were ran in these 2 different machines. We use Cplex as a MIP solver, and we use these parameters. And the sets of instances are the ones proposed by Solomon and Homberger, and the cost of the best node solution on the time of the competition was used for gap calculation, and the primal integral, which is kind of a score from 0 to 10, which not only reflects on our ability to reach the best node solution, but also of doing so in a reasonable amount of time, was calculated by the official controller provided for the competition. So these are the results for the Solomon instances, which are small. So both the primal integrals and the gaps, they tend to be small on these ones. But for the Homberger instances, they start to grow. So there are many sets which are separated by size. So on instances with 200 customers, the results are pretty much similar to Solomon. But as the number of customers grows, both the primal integral and the gaps start to grow too. So as a conclusion, we devised a metaheuristic for solving VRPTW, and we were able to employ different data structures and mechanisms from other works to improve its performance. And although it's really simple, it looks promising because our team was placed 5th among other competitors. And for future work, we intend to improve the SP procedure by, instead of using a MIP solver, trying to use a specialized solver, which should be more focused for that task specifically. And oops, the addition of adaptive features to the ILS metristic, which includes history-dependent, more sophisticated perturbations, and different solution acceptance criteria. So thank you for watching. If there's any questions, I'll be glad to help.